For this last part of Chapter 2, we're going to look at projectile motion. Essentially, it's the same information you had in kinematics from the previous section, but now we're going to look at objects in 2 dimensions instead of simply in 1 dimension. So let's start out with some vocabulary. A projectile is an object that's shot through the air. So we're going to have various objects that we look at, and then also we're going to follow them along a trajectory, which would be the parabolic path a projectile follows. And you'll see, looking ahead a little bit, that we're going to have 2 ways of looking at a trajectory. One, we'll launch something horizontally, and it will follow a path that looks like this, or we'll have something on the ground and launch it at an angle, and then it will make a trajectory that looks like this. So we'll have both half of a parabola and a full parabola as our 2 options, but both of those are called a trajectory. For each of these types of motion, horizontal and motion are going to be independent of one another. So that means that the horizontal motion of a launched ball does not affect its vertical motion. So even if I launch something forward, it's still going to continue to move in a forward direction, even though it's falling as it goes on that path. The second fact, I'm going to put a little star right here. This is really, really important, and you're going to see several multiple choice questions about this on our next test. The only acceleration that you have for a projectile is gravity, and gravity acts in the vertical direction. And we'll talk a little bit more about this as the section goes on. Now, this concept is a little bit counterintuitive to what you might expect, but it is a true statement. An object that is launched horizontally, so one that goes like this, falls for the same amount for each time interval as an object in free fall. So what I have here are 2 pictures. One would be an object that is dropped straight down, and the other one, the object is launched forward and it follows a trajectory as it falls. These dotted lines represent the time intervals, and you'll notice that at each time interval, whether the object falls straight down or goes along the trajectory, that position at the end of the interval is actually going to be the same. So if I were to take 2 objects and launch one straight forward and let gravity do its work, and the other one I let it drop straight down, they would hit the ground at the exact same time. What's going to be new in this section with projectile motion is that when we have a problem, we will break it down into 2 one-dimensional problems. What that means is we're going to look at the horizontal part of the motion and then separately look at the vertical part of the motion. So it's going to repeat material that you've already seen before, but now we're going to do things twice, once for horizontal and once for vertical, and then look at how those are combined together. And then this part's really important. Horizontal motion and vertical motion are connected through the variable of time. And I'm going to ask you about that in the future. So once we get our equations, if we find the time in one dimension, so horizontal or vertical, it's going to be the same amount of time used for the other dimension. These are our 2 equations. They're going to look a little bit different than what we've seen before. We used a generic d for our distances, but now we're going to specify that that distance or displacement is in the horizontal direction with an x, like the x-axis of a graph, and then we're going to use a y to indicate a vertical displacement. So the y and the x are going to tell us a direction. We'll also use those as subscripts to let us know which direction the velocity is. So go ahead and pause the video, make sure you write down what each of the equations are, and then also if it helps you, you can write down what the variables stand for as well. For this particular lesson, we're only going to look at objects launched horizontally, and then in a future lesson, we will look at the full parabola. So in this case, we have a projectile that's launched horizontally, and it's really important to note that it has no initial vertical velocity. So what that means is the Vy, vertical velocity, would be 0. That's going to come in handy later when we do the math. And then also important to remember is that the vertical motion of an object launched horizontally is the same as that dropped from rest. So I have a picture redrawn for you again. If we were to shoot something horizontally, if there were no gravity, it would continue in a straight line. If we were to drop something down, it would follow these dots in this path. And then once we combine them and look at projectile motion, we have the object moving forward and downward. Notice the spacing between each of the dots. So horizontally, those are evenly spaced here, but vertically, the space gets larger and larger as it falls, and the reason for that is because of gravity. Which direction is gravity? Okay, it's down, it's vertical. So gravity is an acceleration, so as it pulls this object down, it's making it go faster and faster as it falls, and that means that it can cover more distance with each time interval as it's falling down. Gravity is not in the horizontal direction, so this remains constant. We have the same velocity and the same distance covered sideways, horizontally, from section to section. You may have seen a similar picture like this on the board. If I were to look at the path of a projectile, okay, it would fall down and look something like this. But if we look specifically at the velocity components, those are the arrows that I'm going to leave up on the board so that you have a visual to look at in class every day. And what those mean are the following. I've made these horizontal arrows red, and these represent the horizontal velocity component. And what I want you to notice is that they stay the same size the entire flight all the way down. Now notice that the purple arrows are vertical velocity vectors, and we start out with 0 vertical velocity, and then notice how the arrows get bigger and bigger. Why do you think that is? Hopefully you said that the vertical velocity is increasing, and the reason for that is because of gravity. So gravity causes the object to actually accelerate downwards, which means it gains velocity. It speeds up as it falls, but because there's no acceleration horizontally, all of those arrows stay the same. And we'll revisit this idea a couple of times before we get to the test. I've got one example problem for us. We've got a stone thrown horizontally at a speed of 5 meters per second from the top of a cliff that's 78.4 meters high. So what you want to do is draw a picture so you can kind of visualize what's going on. So you should have something that looks like this. We're going to list everything that we know. Horizontally, there's a speed of 5 meters per second. That's going to be a Vx because we want to specify it's in the x direction. And then we know that the cliff is 78.4 meters tall, which is this height. And because it's in the vertical direction, we call it a y distance. And then there are two other things we know. How much vertical velocity does it start with? Good, there's none. Okay, and then also we know that the object's going to fall down. So hopefully you know that gravity is the reason that occurs. So we also have an acceleration due to gravity. Now let's work the problem. So I relisted the variables for you. And in the first part, we were looking for how long it takes to strike and hit the ground. What we want to do is use the y equation. The reason for that is because we do not have an x value. So if we don't know x or time, we cannot use the x equation. We're forced to use the y equation. So what I'm going to do is go ahead and plug the numbers in for you. So we've got 78.4. Remember our Vy was 0, so even though it's multiplied by a t here, that whole term goes away, and we're left with half of gt squared on the other side of the equal sign. So I'm just going to simplify that down for you and show you that you get 16 is equal to t squared, and then at the end, don't forget we're looking for just time, and we take the square root of both sides, and you should get 4 seconds that this object is in the air. Part B wanted to know how far from the base of the cliff the stone lands. So as it shoots out and it does this, we're looking for that horizontal distance or displacement. So we're actually looking for the x value. So obviously we should use the x equation to do that. So we've got x equals vxt. and then we plug our numbers in. We had Vx, 5 meters per second, and then in part A we found a time of 4 seconds, and all we need to do is multiply those together to see that the rock lands 20 meters from the base of the cliff. I did want to take a moment to point out that on your test I do give you partial credit. So let's say you get to a word problem and you get stuck and you can't remember how to find time, but you do know how to find the x distance. Go ahead and make up a time. Skip that part A and make up a time value, and then in part B write me a note and say, look, I don't remember how to calculate time, but if I were to have a time and it were, say, X number of seconds, I could plug that in and give you a value. That way you're still getting credit for the second half of the problem and you're not losing points for the entire thing. So remember, I give you partial credit. And lastly, in part C, we were asked to look at the velocity components. So I went ahead and wrote some notes in here for you. The Vx, that's the horizontal component of the velocity, it does not change the entire path. So we started out with 5 meters per second. We're going to end with 5 meters per second. As for the vertical part, remember that the vertical part or component of a projectile is the same as if we were to just drop something straight down. So we can use that knowledge and look at our kinematic equation in one dimension because we can treat it as though we're just dropping it. So to find the Vy before it hits the ground, that would be this final velocity. So I'm just going to move this out of the way and remind you that the final velocity we are looking for is the Vy because it's in that vertical direction. We started out with no velocity vertically, and the acceleration is due to gravity. So what this gives us when we go to plug in would be the Vy, the final velocity we're looking for. It was equal to 0 because it was launched horizontally. There was no vertical component to that velocity. And then we've got gravity and our time of 4 seconds, which we found in part A, and we simply multiply those two together. So remember that the vertical velocity got bigger and bigger and bigger because it actually accelerates because of gravity, and after those 4 seconds, this is how you would find out how fast it's going. That concludes the notes for right now. We are going to pick this up again in the future and look at a projectile where we have the full trajectory. You'll also get a chance to do a lab where we'll go back and practice and use your notes from today, so make sure you have them in class with you as well.